Hey Algebra 1, here are the notes for 9.6, and we're talking about perfect square trinomials. However, before we get into that, I just want to review some of the methods that we have talked about in order to solve the different quadratic polynomials we've worked with. So the gospel according to factoring. We always want to make sure we can't factor out a GCF. Factoring out a GCF usually makes the problem smaller, a little bit more manageable to work with. Next, we want to make sure we can't do any factoring by grouping. This is when we have those four terms, and we factor binomials by seeing what two things have in common. We've worked a little bit with unfoiling. This is that idea that I shouldn't have uppercased all of those, but unfoiling is that idea of what multiplies to C and adds to B. The next method that we learned was difference of squares. Those were something in the form, there we go. Difference of squares was something in the form a squared minus b squared. And we knew that that form was always going to end up as a minus b times a plus b. We also today are going to start talking about perfect squares. So a perfect square is something that has two answers, but they end up being the same answer. So let's FOIL the following. X minus 5 squared is the same thing as x minus 5 times x minus 5. When I FOIL this out, I get x squared minus 10x plus 25. Let's look at the other side. When we have a plus 7 times a plus 7, we get a squared plus 14a plus 49. So what is a perfect square trinomial? And what do you notice must be in place for us to have a perfect square trinomial? So a perfect square trinomial is a quantity times itself. So notice, this is the quantity. When we FOIL it, we just multiply it by itself. Same thing over here. The quantity x minus 5 squared is the same thing as saying x minus 5 times x minus 5. Now, what do you notice has to be in place for us to have a perfect square? Well, the middle term is doubled. So middle term is doubled. Notice 7 turns into 14 when we double it. And the last term is squared. Last term is squared. So the 7 turns into 14 in the middle term. It turns into a 49 in the last term. Here, we double negative 5 to get negative 10. We square it to get 25. So, factor the following. If we notice that something is a perfect square trinomial, we can immediately go backwards. Notice 10 is 5 doubled, and 25 is 5 squared. Because this fits our perfect square trinomial format, we know that it's m plus 5 times m plus 5. And I can FOIL that back out to double check myself. However, I don't really need to in this case. The second one looks a little bit harder because it's in the wrong order. However, it still follows all the rules. Personally, I'm going to rewrite it so that it's in standard form, because this allows me to see that 18 is 9 doubled. Oops. Nope, this should have been... My apologies. I got a little gung-ho with my writing, and this definitely should have been 5 times 2. And this should be 9 times 2. Because if we multiply it by itself, that's squared. And that's not what the middle term actually says. So that'll be 9 times 2, and then the end would be 9 squared. When I notice this, I can immediately put it in the form d plus 9 and D plus 9. So this should be a 2, and that should be a 2. All right, let's check out some more on the back. First, let's ask ourselves, when we're solving perfect square trinomials, we do things exactly as we've learned thus far. So, is this a perfect square trinomial? What is this doubled? Well, that would be negative 3 times 2. Hopefully, 9 is negative 3 times negative 3. Since it follows our rules, we get to write it as x minus 3 times x minus 3. And then it says when we're solving, we just use the ZPP just as we have. We set x minus 3 equal to 0, and we set x minus 3 equal to 0. Now you'll notice because they're the same factors, we end up with only one answer. And this one answer has a special name. It's called a double root. Because we have it 2 times, it's double. All right, let's keep going with this. These are perfect square trinomials because the middle term is 2 times 2. The third term is 2 squared. So I can put this as x plus 2 and x plus 2. I notice because it's set equal to 0, I have to solve. So when I solve one side of these, I get x equals negative 2. Same thing here. Is this a perfect square trinomial? Well, not quite yet. However, if I go back to the other page, remember, sometimes we have to use a different method before we can use the main method. So in this one, I notice these are all divisible by 4. So I'm going to factor out a GCF of 4 to make my problem look a little bit smaller and a little bit more manageable. When I do this, I now notice this is a little bit nicer. This becomes 2n plus 1. This becomes 2n plus 1. And it equals 0. But I don't forget to bring that 4 down. This could be a perfect square trinomial or an X puzzle. Completely up to you and what you're more comfortable with. I've been working at this a while, so I can just notice this. But if you need to do the X puzzle, please don't hesitate to do that. Use those methods that you're most comfortable with. Now, when we do this, we have 3 things that we need to set equal to 0. But you'll notice when we set 4 equal to 0, that's not a true solution, so we don't pay attention to it. When we set our second root equal to 0, we notice it's the same as our third. And when we solve, we end up getting n equals negative 1/2. And it would be the same thing for that second root. So notice, this section also mixes in the other factoring techniques that we've talked about. So let's mix some of those up together and see how good we are with recognizing what needs to be done. So factor the following. I would like you at this point to pause the video, give these a try, and then come on back to see how well you did with them. All right, hopefully you paused the video and tried these on your own. When I look at this first problem, I automatically notice that they have a 4 in common. My gut reaction is to always factor out the GCF if possible. When I do this, I notice that I now have that difference of squares that we've talked about before. So I can factor this down to a k and a k, a 5 and a 5, an addition and a subtraction. The next one's a little less obvious because they don't just have the first number in common. I have to recognize what these are all divisible by. I'm pretty sure it's just a 2, so let's factor that out right away. I factor it out, I get 10n squared plus 17n plus 3. All right, that one's really tricky. There's a number out in front, so I'm going to go to my X puzzle method. 10 times 3 is 30. The middle term is 17. What are my options here? Well, I know 15 and 2 will multiply to 30 and add to 17. So I'm going to bring that down and rewrite it as 10n squared plus 15n plus 2n plus 3. Yeah, that looks good. I notice I have to use a factoring by grouping technique, so I'm going to split these down the middle and say that these two have a 5 in common. So when I pull that out, a 5 and an n actually, I'm going to be left with 2n plus 3. These don't have anything other than a 1 in common, so I factor out that 1 and also get a 2n plus 3. When I put all of this back together, I get 2 outside of 2n plus 3 times 5n plus 1. So this method actually used GCF, and XPuzzle, and a factor by grouping in order to get to our final answer. You can see how some of these problems can be a little bit long and challenging, but totally doable if we're willing to mix our methods together. All right, next one on the list. We've got an x squared plus 6x minus 9. This one doesn't look awful, and I think I'm just going to stick to our first method that we learned, which is what multiplies to C and adds to B. Except, upon looking at it, I can't actually use that method because I can't think of anything that would multiply to -9 and add to a positive 6. And when I look at my other methods, there's no GCF, it's not a perfect square trinomial, and it's not a difference of squares. So this one is actually prime. And there are going to be those problems that no matter how many techniques you throw at it, it still can't be solved. All right, right off the bat, I see this one as 4 terms. That's a lot of terms to work with, so I'm just going to start by factoring by grouping. The first two I notice have a y squared in common. When I factor that out, I get x squared minus 1. The second two have a z squared in common. When I factor that out, I'm also left with an x squared minus 1. When I put that back together, I get x squared minus 1 times y squared plus z squared. I notice I can't really do anything else with the second term. However, the first is a difference of squares because both x is squared and 1 is squared. So I can break that one down into x plus 1, x minus 1, and leave the second term alone since nothing can be done with that. Remember, we don't work with sum of squares yet, only with difference of squares. I've double checked myself. There's nothing that can be broken down further. So this is my final answer. All right, remember what I said at the beginning of this unit? The only way to get better is practice. Practice doesn't necessarily make perfect, but it does make permanent. So make sure when you're practicing, you're double checking yourself as you go along to make sure that you're doing things right and you're not practicing something incorrectly, because whatever you practice will become permanent. All right, go get some practice in. Let me know if you have any questions.